Chapter 9 is on nuclear chemistry. So in order to help us understand radioactive isotopes, we're going to do a little refresher on what an isotope is that we learned previously in the semester. So an isotope, again, it's an atom that has the same number of protons. So we're talking about an element. All those atoms within the element have the same number of protons because that gives it the identity, but they can vary in the number of neutrons within those atoms from one atom to the next. So their mass numbers are going to be different. So mass number, again, is protons plus neutrons. When you write your isotope symbol, your mass number is located at the top. Another way we write that sometimes is we could do the symbol H for hydrogen dash 1. The 1 would also be our mass number. So there was two ways we learned how to write mass number. And then atomic number is the number located at the bottom. So here I have three different isotopes of hydrogen. Again, they all have the same atomic number because they all have one proton, because proton tells us the identity. So they all have one proton, so they're all hydrogen. But their masses can vary. How heavy are they comparing one to the other is going to be determined by the number of neutrons. So let's look at these three different isotopes of hydrogen. We have H1, H2, and H3. So in the first one, let's just start by identifying the number of protons. All of them have one. And then our number of neutrons we can figure out based on the mass number. So again, mass number is given as 1. That's going to equal to our protons plus neutrons. So if we have one proton, we have 1 is equal to 1 plus n. N must be 0. So in the next one here, our number of neutrons, again, our protons is 1. Our number of neutrons is going to be 2 is equal to 1 plus n. N is going to be 1. And then in the last one, again, we have 3 is equal to 1 plus n. N is equal to 2. So we determine the number of neutrons for each one of these different isotopes of hydrogen. Next question is which one is going to be the heaviest. Again, the mass comes not from electrons, but it's your protons and neutrons. They're each about 1 AMU. So in this H3, we have 1 proton and 2 neutrons. This is going to be obviously our heaviest one because it has the most amount of protons and neutrons. And H3, it's also known as tritium. And tritium is what they call water at nuclear power plants because this hydrogen is incorporated into the water molecule, and they sometimes call that heavy water. So of the three isotopes of hydrogen, H1 and H2 are stable isotopes. H3, tritium, is not stable. It's an unstable isotope. The reason is there's too many neutrons for it to be stable, so this is actually radioactive. This is a radioactive isotope of hydrogen because we said here our protons, all of them are 1 for hydrogen, and then in this case, the neutrons here were 2. So in order to be stable, the proton to neutron ratio for elements, when their atomic number is 20 or less, this is sort of a general rule of thumb, it's a 1-to-1 ratio. So in this ratio here of our protons to neutrons, we have a 1-to-2 ratio. Versus if we look at, for example, H2, that has 1 proton to 1 neutron. So we have the 1-to-1 ratio here, which is stable. Here it's 1-to-2, so that's not stable. So what happens is the neutron can actually be emitted from my hydrogen atom and converted into something else, which is our radiation. So there's a number of different types of radiations we'll be learning about, and beta emission is the first one we'll be learning about, where that neutron is actually converted into something else. This chart is showing us our proton to neutron ratio that makes elements stable. So as I said, if your atomic number on our x-axis here is the number of protons, which is your atomic number, is 20 or smaller, you can see on this chart that the ratio of 20 protons to 20 neutrons here, it's about 1-to-1. So this is our stability that makes isotopes of different elements stable when they have that 1 1-to-1 ratio of protons to neutrons. As you get up into the higher weight elements, when you're going above 20, then the ratio changes where you can have more neutrons to protons and you're still going to be stable. So that's why this kind of veers off. The red line here is 1-to-1, and we veer off here because as the atoms get larger for our heavier weight elements, they can handle more neutrons in there. So they can be stable with more neutrons than protons. There are 3 types of radioactivity that we'll be learning about. The first one is beta emission. Beta emission occurs when we have a radioactive isotope that has too many neutrons compared to the number of protons in its atom. And so what it can do is it can actually convert one of those extra neutrons into a proton and a beta particle. Beta particles are high energy electrons. They're symbolized by E, which stands for an electron. Electrons have a mass of 0 essentially, because we learned earlier that protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, and electrons about 1/2000th the size, so it's very small in comparison, so we just say it's negligible. And then electrons have a -1 charge, which we usually write our atomic number at the bottom, so an electron we just put -1, which you can remember electron has a -1 charge. So you want to remember this symbol for writing a beta particle. So essentially what happens is we have here an atom that is a radioactive isotope of whatever element it may be. And that radioactive element has too many neutrons, so it's going to convert one of those into a proton, and when it does that, the neutron turns into a proton plus this high energy electron, which is our beta particle, that flies out of here. And we have now created actually a new element because it has a different number of protons. So what's interesting when you're writing nuclear reactions, which we'll do some examples coming up, is we balance the mass number, which are the numbers written at the top of our reactants, must always balance the mass number of our products added together. So in this case, we have 1 for our neutron on the left-hand side of our reactants, and then we have a 1 plus 0 for our protons and electrons together. So if we add that together, that's 1. So 1 and 1 balance for our reactants and our products for the mass number. And then our atomic numbers at the bottom. So a neutron doesn't have an atomic number, so it's just 0. Proton, remember atomic number means how many protons you have, is 1. And then electron, we have -1. So we have here 0 is equal to 1 minus 1, which is also 0. So our atomic number is balanced as overall, as well as our mass number for reactants and products. So beta particles are these high energy electrons that are given off by radioactive isotopes. Carbon-14 is a radioactive isotope of carbon. The type of emission it gives off is beta. And what happens in this is, again, a beta particle is emitted from our isotope carbon-14, and a beta particle is this high energy electron. So what happens here in our carbon-14 atom, our mass number is 14, so we can figure out our number of neutrons. The atomic number for carbon is 6, and it's represented by this red sphere with a positive sign in the center for protons. And carbon-14 is the mass number again, so 14 minus 6 gives me 8 neutrons. So when we have elements that are atomic number 20 or less, our rule says that they want to have a ratio of protons to neutrons of about 1-to-1. So we're 6-to-8, so we have too many neutrons. So this neutron can be split into a proton, which stays in your nucleus, and then eject that high energy electron, which is our beta particle. So that's what's being represented here. Here's our beta particle, which is our high energy electron. And what happens here is that neutron was converted. So we had 8 neutrons. Now we can see we have 7 neutrons. And we had 6 protons, and that neutron was converted into a proton in the electron. So now we have 7. So this is showing you, again, an example using carbon-14, a radioactive isotope, how it gives off beta emission. This example shows how we would write a nuclear equation for carbon-14 emission, beta emission. So what we're looking for here is we're always going to be given our radioactive isotope. In this case, it's carbon-14, this radioactive isotope of carbon. If we had, a sample of carbon, some of those isotopes are going to be radioactive. Most of them are probably not. So carbon-14, again, we know carbon's atomic number is 6, and its mass number is written at the top is 14. So I would always tell you what type of emission it's giving off. So in this case, it's a beta emitter. So we need to remember to write the symbol for the beta emission is E, representing our high energy electron with no mass, so 0 at the top, and then -1 to represent the -1 charge. So what we're trying to determine when we write a nuclear equation is what is the new product that carbon is decaying into. So when you're writing nuclear reactions, what you're essentially doing is balancing the mass at the top of your reactants on the left and your products on the right. So on the left-hand side, we have 14 for carbon. So on the right, it must balance. So 14 minus 0 is equal to 14. So our mass is balanced for our products and our reactants. At the bottom in our atomic number, carbon has atomic number 6, and we have the atomic number -1 represented for our electron here. So we need to know the atomic number of the new element we've created. It's always going to be 1 larger than the original atomic number. So 7 is 1 larger, and if we look at 7 minus 1, that equals 6. So our atomic numbers are going to be equivalent on the reactant side and on the product side overall when they're added together. So then we can determine what is this new product that we created. So we use our atomic number 7 to determine that, and atomic number 7 is nitrogen. So now we know that our new element, what we created. And then we can also check our proton to neutron ratio here. So in carbon, we have 6 protons. Our number of neutrons is 8. And in nitrogen, our number of protons is 7. And now we have 14 minus 7, so our number of neutrons is 7. So our proton to neutron ratio here is 1 to 1. So we have now created an atom that is stable versus carbon-14, which was radioactive because, again, too many neutrons compared to our protons in this example. So as an overview to remember whenever you're doing beta emission, that the new element that you're going to be decaying from our radioactive isotope down into is always going to have an atomic number that's 1 greater than the original radioactive isotope and the same mass number. It's not going to change. For this nuclear reaction, we want to determine for phosphorus 32, what is the reaction product? And phosphorus 32 is a beta emitter. So whenever you have a beta emitter, the first thing you want to do is write down that symbol for our beta emitter, which we know is E, stands for our high energy electron with no mass, and -1 written as where our atomic number would be. And then we're trying to determine what's the product we're creating. So for beta emission, the mass number doesn't change because 32 plus 0 equals 32. My atomic number is always going to be 1 greater than what I originally started with. So 15 plus 1 gives me 16. And then again, we can check here that 16 minus 1 equals 15. So we have atomic numbers balancing out. Now we just have to determine the identity of our new element that phosphorus 32 has decayed down. So we use our periodic table to see which element has atomic number 16, and that would be S for sulfur. In this example, samarium-151 is a beta emitter. We want to determine what is the new reaction product when samarium-151 decays into a new product. So let's start by writing our beta particle, our high energy electron, mass of 0, and then we're going to determine the mass of my new product. So it's always going to be the same number because it's 151 plus 0. We have 151 for our mass number, and then the atomic number is always going to be 1 greater, so 62 plus 1 gives me 63. And then I use my periodic table to determine the element with the atomic number 63, which is europium, EU. And europium was discovered in Europe. So this is showing me what samarium 151 decays down to when it gives off a beta emission is europium. The next type of radioactive emission we're learning about is alpha emission. In alpha emission, a helium nuclei is ejected by our radioactive isotope. And in this case, the alpha particle is represented by helium as our element symbol. Helium has an atomic number of 2 and a mass number of 4. So our number of protons in this case is 2, and our neutrons is 2, because our mass number is the protons plus neutrons. So looking at our atom over here, this is our radioactive isotope. And what happens here is we give off this alpha particle. And when we do that, what we're doing is losing 2 protons and 2 neutrons. That's what makes up this alpha particle. So the red spheres represents our protons and the gray spheres represent our neutrons. So this is showing 2 protons here to 2 neutrons. And so we end up creating, again, a different element than what we started with. So the radioactive isotope decays into a different element that's going to be more stable, and it's going to have a different number of protons and neutrons than we originally started with. So in our example here, we have uranium-238, which is a radioactive isotope of uranium. And we're going to do the same thing we did in the previous beta emission example, where we're going to balance the mass number at the top and the atomic number at the bottom. So uranium-238 is our reactant on the left, and we need to balance when we create our new product on the right. So our mass number of helium in this case must be subtracted. So we have 238 minus 4, and that equals 234. That's the mass number of our new element. And then the atomic number, we started with 92, so we're going to have 92 minus 2 to tell us the identity. Atomic number is 90, and if we looked on our periodic table, the atomic number with 90 is thorium. So an overview here to show you whenever you're doing alpha emission is the new product that you're creating for alpha emission is always going to be, it's a new element. The atomic number is always going to be 2 less than what you started, and the mass number will always be 4 less than the original radioactive isotope you started with. Here we can see uranium-238, which we said is a radioactive isotope, decaying to thorium-234. Sometimes when they decay, they decay into something that's stable. Sometimes they actually decay our radioactive isotope into another isotope that is still radioactive. So this is showing you with uranium-238, once it decays to thorium-234, that's still radioactive. That's going to decay into another isotope, and it's going to keep going until eventually we get to something that's stable, which down here in the end of this chain is lead-206. Pb is lead. And with these different radioactive isotopes, they can give off different types of radiation. So the red arrows here represent alpha decay. The blue arrows are representing beta decay, the 2 types of radiations we just learned about. So as far as giving you a radioactive isotope, I always tell you if it's an alpha or a beta decay, or the third type we're going to be learning is called gamma, in order to write nuclear reactions. In this example, we have polonium-210 is an alpha emitter. We want to know what the new reaction product is. So the first thing we always want to start with is writing our symbol for an alpha emitter, which is something you need to remember. Helium, and the mass number is 4, atomic number is 2. And then we're determining the mass number of our new product. So it's always going to be 4 less than the original reactant. So it's 210 minus 4 to determine our new mass number for our new element. So that will be 206. And then the atomic number, which will tell us the identity of our product, is going to be the original atomic number minus 2. And that would give us 82, and then we would use our periodic table. And if we look up on the periodic table, atomic number 82 gives me Pb, which is lead. You don't have to remember the name lead, but just know the symbol. You have your periodic table to determine that. So again, we can look at our overall mass numbers at the top. They should balance. 206 plus 4 equals 210. Atomic numbers at the bottom, we've got 84 in the reactant, is going to balance 82 plus 2 in our products on the right. And this again is showing me down here what's going on. This is representing my radiation here. This is my radioactive isotope of polonium. It's emitting this helium nuclei, which contains, again, my 2 protons and my 2 neutrons. And then what I'm left with here is lead 206. Here's another example of an alpha emitter. We have actinium 222. We want to know what the reaction product is after it undergoes alpha emission. So again, first thing we do is we write down our alpha particle, which is helium 4,2. And then we determine our new mass number. So we have 222 minus 4 gives us 218. And then atomic number is going to be 89 minus 2 will give us 87. And then we use our periodic table. Atomic number of the element number 87 is francium, discovered in France. So this is my new reaction product, francium. The third type of radioactive emission we're going to learn about is gamma emission. Gamma emission are not particles like we learned with alpha and beta emission. They're actually rays of electromagnetic radiation. And their electromagnetic radiation travels in this wave formation that's illustrated down here. So what we're doing here is we're showing this high energy nucleus right here, this first one, Pu, and this one is going from a high energy state. It gives off these waves, which is our gamma radiation, and becomes the same element, not becomes, stays the same element, same mass number, same atomic number. It's just in a lower energy state. This energy was given off, this electromagnetic radiation. So writing gamma emission nuclear reactions are the simplest to do because, as you can see here, our mass numbers don't change and our atomic number does not change. So for boron, the atomic number tells us we have boron is 5, does not change. And all we have to do is remember to write our symbol for our gamma ray, which is symbolized by this gamma. So releasing a gamma ray does not change your element, mass number, or atomic number. All you have to do is remember how to write the symbol for a gamma ray. So a gamma ray, as we said, is a type of electromagnetic radiation. So I want to talk for a bit about what is electromagnetic radiation. So there's all different types, like you have radio waves, you have microwaves. They're all forms of electromagnetic radiation. The way they differ, as I said, electromagnetic radiation travels in waves, is by the distance of what we call their wavelength. So the wavelength, as we're looking at the picture down on the right here, we have a wave, like imagine you're at the ocean. The top of the wave is called the crest. The bottom of the wave is called the trough. You don't have to remember the names, the crest and the trough, but realize the top and the bottom. The cycle from one top to the next top of a wave is called the wavelength. And we can measure the distance. And it's the differences in the distance that gives us different types of electromagnetic radiation. So your wavelength, again, is the distance between the top of two waves, also known as a wave crest. And you can find in your textbook the electromagnetic spectrum that shows you different types of electromagnetic radiation and how they vary with wavelength. This chart shows us the electromagnetic spectrum. And basically what this is showing us is different types of electromagnetic radiation and how they vary in their wavelength. So we have in the chart here, it's showing us here the wavelength in meters. So radio waves, we have 10 to the third. So again, that's 1,000 meters. The distance between the top of the wave crest to another one. So it's very long distance for a radio wave. And as we go across here, the next type of electromagnetic radiation is a microwave. And notice now we're at 10 to the negative 2 meters. So that's a much smaller distance. So they're going to get shorter and shorter as we go across. So when we go to infrared, it's a smaller number, visible, UV, X-ray, and gamma rays. Gamma rays have the smallest wavelength. So that's how one type of electromagnetic radiation differs from the other, is based on the wavelength. So we can see in here we go from radio waves with a very long wavelength to our gamma rays with a very short wavelength. Again, 0.00, that's a whole bunch of zeros going off my screen until I would get to 10 to the negative 12th. I do want you to know the types of electromagnetic radiation listed on this chart, which is also in your textbook. And you don't have to remember the exact numbers of how long their wavelength is, but I do want you to know the longest to the shortest. So going from radio waves all the way across to gamma rays, I want you to remember these different types of electromagnetic radiation and which one has a longer wavelength and a shorter. So if I was to ask you a question, for example, does a microwave or does a gamma ray have a longer wavelength? Wavelength, that's the symbol for a wavelength. So again, that's the type of question I might ask you, and obviously the microwave has a much longer wavelength than does a gamma ray. So this chart again shows us the wavelengths of the different types of electromagnetic radiations. So again, starting on our left here with the longer wavelengths, we have our radio waves, which is how we have like AM, FM radio when we're listening to the radio. Then we go to microwaves, which microwaves basically can be used to heat up water when you're cooking your food. So the food heats up and your container does not heat up. Also used in cell phones and other areas. Infrared is heat. So infrared heat you might get from sun, fires, etc. This picture down here is showing infrared heat is used in night vision. So at night, it's detecting the body heat from these soccer players down here. So this is showing a photograph, a regular photograph, and then this one is using night vision where it detects the heat. Visible light, that's from the sun, or sunlight, or lights from the, light bulbs. And that also can be diffracted using a prism into the colors of the rainbow here. Ultraviolet light, again, we get from the sun. Our UV light is why we wear our sunscreen to protect our skin from the UVA and the UVB rays from the sun. And then we have X-rays, which we know we can use in the medical area. And then gamma rays that we're learning about in this chapter and nuclear chemistry are used also in medicine for killing cancer cells. So this is the chart is the same as just written in the opposite direction. So our wavelength here is going from shortest to longest. So we would have our gamma in this example on the left and our radio waves on the right. Same thing, it's just written in the reversed order. The charts can be done either way. But what I wanted to show you this with our increasing wavelength, we have the opposite effect. We have increasing energy going the opposite way. So what this is telling us is our gamma rays that have the short wavelengths have the highest energy. And it's the higher the energy, the more damaging that electromagnetic radiation is. Versus we have the lowest energy on the right here for our radio waves. So again, if you turn on the radio, you don't think about, oh, I'm going to be hurt by listening to the radio. It's not going to damage you at all. Versus, we get to the point where we're going to get to visible light. Again, that's not going to hurt us down here. But once you get to UV, okay, UVA, UVB, those can definitely damage your skin and can lead to cancer as well. And that's again why we wear our sunscreen to protect us from those UV rays. So that's going to be once you get to the damaging point is once you get here. So they have higher energy over here. Higher energy, the more damaged they are. X-rays, again, they start destroying biological molecules with excessive exposure and can actually cause cancer as well. And then gamma rays can also cause cancer. and they're the highest energy of all. Remember, they have that really, really short wavelength, like 10 to the negative 12, very small. The other thing I wanted to point out here is we said visible light. If you use a prism, you can diffract it to get the colors of the rainbow down here. So one way you can remember the colors of the rainbow, which you may have learned this before, is Roy G. Biv. And I do want you to remember that. So it's the opposite way we're going here. So this would be R is for red, orange, Y is your yellow, G is your green, blue, I is indigo, and then V is our violet. Okay, so what I want you to remember with the colors of our visible light is the wavelength. So in this one we have red is the longest wavelength to violet as the shortest wavelength. So know the comparison of the different colors, which one has the longest wavelength to the shortest wavelength. So out of this chart I want you to realize, longest, again that symbol is wavelength, the lambda symbol. Longest wavelength to shortest for the different electromagnetic radiations, and then also the energy involved. E is energy. So I may ask you, for example, does red light or green light have higher energy? Okay, so again, you're going to know based on the wavelength. The shorter the wavelength, the higher the energy. So green light will have my higher energy. So again, the shorter your wavelength, the higher the energy. So here's an example showing us again our gamma rays, which have a very small distance between the wave crest. So they have a small wavelength. Okay, that's our first one represented here. So they have very high energy, high penetrating power. They're going to be more dangerous to you. They could cause cancer. Visible light has a much longer wavelength. So that compared to a gamma ray, which is the one at the top. So longer wavelength means lower energy. And again, visible light is not something we're concerned about. It's not dangerous at all. So you can have radioactive isotopes that give off more than one type of emission. For example, radium-226. It's an alpha and a gamma emitter. So again, if you have a gamma emitter, all you have to do for that is just write the gamma symbol. So if you were asked to write a nuclear equation, you would just write your gamma symbol here. And then alpha, we learned before, the alpha symbol is my helium-4. So I would write that. So here's just an example that's written out for you. You basically would determine your new product. So radium-226, when it decays, it gives off the alpha particle, the gamma particle. The new product it's creating, we'd only have to balance based on my helium. So we have 226 minus 4 equals 222 to give me my mass number. And then I have 88 from my original radium minus 2 equals 86, and that tells me the identity of my new element, which is radon. Now, radon is actually kind of interesting. This is a radioactive isotope that is a gas. And if I was to ask you the #1 cause of lung cancer in the United States, you all know that it's smoking. This is actually exposure to radon-222 is the second leading cause of lung cancer in the US. And the reason why is we have this naturally occurring. So radium-226 comes from the Earth's crust. It's in rocks, etc. And when it decays, it gives off this radon gas. So this is something that's found in the environment. It's naturally occurring. And when you inhale, you're getting it into your lungs. So now we have this radiation that can get into your lung tissues in there and cause cancer to start developing. So it depends on where you live as to how much you're going to be exposed to. So in the United States, like in the Rocky Mountains area, in the central part of the United States, they have much higher levels, and it's primarily because of the geology that makes up the area. And what happens too is when they build houses in the Midwest, they have basements. Okay, so here's my house, and then you have basement underground. And so this house is built here on this naturally occurring our Earth here. Radon is being exposed up into the basement. And so in the basement, we don't have any ventilation. Whereas in California, there's not very many basements around. You have windows that you can open, you can let this gas out, you're not exposed to very high levels. But if you were in a house with the basement and you went downstairs and there was no ventilation, you could have a higher buildup of radon down here. So there was actually a housing tract that was built in Colorado. And after they built the housing tract, they went and tested the air to determine the concentration of radon. And they found the levels were so high in this housing tract that they had to basically abandon the whole housing project, and the developers lost a lot of money with that. So you can actually test your house for the radon levels. I remember being in college taking nuclear chemistry, and I bought one of these test kits at Home Depot, and I went and tested my house. Again, this was in California, and the radon levels, there's a cartridge that takes the air sample, you send it to a lab, they test it for radon levels. It was below anything that would be hazardous, so it wasn't a problem. But it might be something, if you're buying a house, that you might want to consider yourself, is you want to test it and see what are the radon levels in that house. Maybe they might be high enough that would be a concern. And again, it depends on where you live, what part of the world, and what the geology, the makeup is. And again, if you're being able to have airflow through your house to dilute it out, or if you have high concentrations. So this table is an overview of the 3 types of radiation we're learning about. There are other types of radiation like positron emission that we're not going to be covering. So these are the 3 I want you to know are the alpha, which would be symbolized by helium-42. We have beta, symbolized by our 0, -1, E, and then our gamma symbol down here. So know the symbols for those. The mass of an alpha is actually, much larger, is 4 because it's 2 protons to 2 neutrons. Beta particle is that high energy electron, so it has a very small mass. It's about 1/2000th the size of a proton. And then a gamma is not a particle, so it has no mass at all. You don't have to know any common sources. Penetrating power. This basically is if you're thinking about your skin, your body, how far these particles would be able to get into your skin. The alpha particle is going to be able to go in the smallest amount because it is the largest. And then the beta could go in even farther, and then the gamma rays, because it's not even a particle, it's very easy to penetrate your body. This picture here shows us our penetration powers of our alpha, beta, and gamma. So the alpha, again, remember the larger particle with the 2 protons and the 2 neutrons. You can actually stop it from entering your body with just a piece of paper. So if you are wearing clothing, that's going to protect you from alpha particles. Beta can go through a piece of paper and can hit your skin and maybe just kind of go a little bit into your skin. Versus gamma, which again, it's not a particle, can go right on through paper, right on through your skin, but you can block it with concrete, depending on how thick it is. So that's, again, if you think about a nuclear power plant, they build these concrete walls, this big dome that would go over it with your nuclear reactor on the inside to protect that radiation from being able to come out.